Hello, everyone. My name is Ray, and I'm from LLM team of Anyscale. This is Yongji. He's from UC Berkeley. Today, we're going to talk about the elastic expert parallelism for vLLM. In this talk, we will first talk about the background. This includes mixture of experts, expert parallelism, the challenges for large and wide EP, and then we will present the elastic expert parallelism for vLLM. After that, we will dive into the efficient scaling techniques. And in the end, we will talk about the roadmap for this project. So in this talk, you will learn about the vLLM elastic EP architecture, the elastic scaling processes, and how to achieve low overhead scaling. So let's first look at mixture of experts architecture. We know that for a transformer layer, there is the attention layer followed by FFN layer. And for MOE, we replace this FFN layer with a set of specialized FFNs called the experts and the router. The expert is basically a neural network that contains a subset of the trained parameters. And the router is a gate network with also trained parameters that determines which tokens to route to send to which experts. After the tokens are routed and the matrix multiplications are performed at the experts, the results are summed, weight summed together, and they are sent to the next layer of attention. Sorry. So there are several benefits of MOE. First is its sparsity. We only activate a subset of the experts per token. That means it's more efficient than the dense architecture. It also has better scalability because it drastically scales up the model and data size with the same compute budget. And then what is expert parallelism? EP is basically a type of model parallelism that distributes the experts across multiple GPUs. In this figure, we can illustrate the concepts of EP. On the left side, if we don't have EP, then the experts are located on the single GPU. But if we have EP with size 4, for example, each expert can be located on its own GPU, and they can be processing the tokens in parallel after the tokens are routed to them. Modern MOEs are large. That means they have large number of experts and also parameters. Typically, there are hundreds of experts and hundreds of billions of parameters, or even 1 trillion parameters, most of which are just MOE parameters. Large MOEs often use wide EP, which means there are fewer experts per GPU. Usually, this is just 1 to 2 experts per GPU. And with this, it improves the jam efficiency and weight reuse, and it avoids the memory pressure from many small experts when they are sharing the same GPU. With wide EP, we're essentially scaling out to more GPUs and nodes. There are a few challenges associated with large and wide EP. The first is the scaling unit is monolithic. This means that we need to deploy or scale the model at model level as opposed to expert group level. For example, if we have online workload and the traffic increases, and we want to scale up, one option we have is to deploy another model replica, which essentially replicates everything. But the downside is it has low cost efficiency because we don't necessarily need to replicate the whole model to just serve a very limited increase in the traffic. The other option is we can redeploy the same model replica with a new parallelism configuration. In this case, we deploy with EP size 5. But the downside of this approach is it has long service interruption time because the restart usually takes time because we need to reload the model weights, we need to capture the CUDA graph, and there are many steps involved. This typically takes several minutes to finish. Another problem is fault tolerance, because when we have more GPUs and more nodes, this typically means we have higher chance of failures. And a fault on one GPU could result in the service interruption of the whole model. And this, of course, affects user experience. To address these challenges, we develop elastic expert parallelism. It offers elastic and fine-grained scaling at expert group level. This means better cost efficiency to adapt to the dynamic load, online load. And it also scales faster. Elastic EP also enhances fault tolerance when we introduce the mechanisms to detect, confine, and recover from the faults on individual GPUs. And we can optionally scale up to the original size after the fault tolerance. Here's the architecture for elastic EP in vLLM. Let's say we have initially 4 engine cores that are serving traffic, and as shown on the upper right corner, the blue boxes, and they are located on 2 different nodes. And we want to scale up to 6 engine cores. So we first issue a command to the API server, and which forwards the request to the engine client. And then the engine client triggers the reinitialization on all the existing 4 engine cores with the new EP size 6. In the meantime, the engine core manager also interacts with Ray cluster to bring up 2 new engine cores. And also it specifies the new size as 6. The engine client also needs to call the reconfig into this coordinator, which is responsible for the request wave coordination, and because we need to update the information about all the engine cores. So as you can see from the last slide, there are 2 major functionalities we need to support elastic EP, namely engine orchestration and state management. For engine orchestration, in the case of upscaling, we need to bring up additional engine cores. And in the case of downscaling, we need to tear down a subset of the engine cores. And we use Ray-based orchestration. And in this case, each engine core is essentially a Ray actor. For state management, the states are distributed in different components in vLLM. This includes the coordinator we just talked about, and also the engine core, which has the data parallel communicator. And GPU worker also contains a lot of states. This includes the distributed environment and the communicators. It has the model weights and the CUDA graphs. Let's cover a little bit more about the expert weight update. So we can essentially use EPLB for this purpose. And EPLB is expert parallel load balancing. It's a mechanism for rebalancing the expert distribution on the GPUs where workload characteristics change. And EPLB for weight transfer, we can use EPLB for weight transfer during the scaling because it's faster than the loading from disks or the remote storage. So here's an example that we do EPLB reshuffle during scaling down. Let's say the first engine core is going to terminate, and there are some expert weights on this engine core. And we first determine a global picture of all the experts and deduplicate the experts. And then we do a reshuffle so that the necessary experts are moved to other engine cores. So next, we are going to dive into the elastic scale-up process. Let's first talk about the what happens for existing engine cores. Let's use the same example that we want to scale up from 4 to 6 engine cores. So maybe the graph is a little bit small, but I'll explain it. When the vLLM engine first receives the request, it will forward this request to all the existing engine cores. And then the existing engine cores would trigger the reinitialization on all the GPU workers. The GPU worker would do a bunch of things, basically to reset up the environment to accommodate to adapt to this new AP size. It will first destroy the old distributed environment and the communicators, and update the parallel configuration. And then it reinitializes the distributed environment and the communicators. It also reconfigures the MOE, and finally run the EPLB reshuffle. And what happens for the new engine cores? Basically, they, when the vLLM engine will first interact with recluster to create new engine cores, and then it will start up the new engine cores. This is a very similar process as a normal startup, but one key difference is that on the GPU model runner, it needs to first receive the dynamic EPLB information from the existing engine cores before it loads and before it can properly load and reconfigure the model. For elastic scaling down, let's use an example of, we want to scale down from 6 engine cores to 5. And in this case, the vLLM engine first determines that we have 5 engine cores to keep and 1 engine cores to terminate. For each of the engine cores to keep, it will call reconfiguration. It will first run the reconfiguration, which is very similar to the one that's used in the scale-up process. But we run the EPLB reshuffle first. And then for the engine cores to shut down, it will also, we send this reconfiguration request, and it will first run the EPLB reshuffle before it actually cleans up the distributed communicator and also shut itself down. And next, I'll hand off to Yongji to talk about elastic scaling optimizations.
Okay, thanks, Ray, for giving us an intro or an overview of our elastic EP effort. Now I will talk about some of the ongoing optimization we are currently working on. So to achieve practical scaling that is really useful in practice, right? We actually need to minimize the overhead from 2 perspectives. The first one is we want to minimize the downtime of existing workers. We want them to continue to serving in-flight requests with negligible disruption, right? And otherwise, it's basically we have no benefit compared than restarting the whole instance from scratch. And the second part is that we want the new workers to quickly complete boot up and join the existing inference group as soon as possible so they can handle bursty load. Let's first take a look at the first part, how to minimize the downtime on existing workers. So here the challenge is how can we asynchronously set up the corresponding communicators and, for example, transfer weights to the new workers. We also need to support QDA graph with updated configuration that included the new set of kernels, and we also need to allocate the new communication buffers. And I will talk about this in detail later. Let's first look at the existing workflow and what the current problem is. So basically, in our current workflow, after scale up or scale down command is issued, we will initialize the EP communicator and send the weights of the attention layers to the new workers in the case of scaling up. And we will reshuffle the export with EPRB. And after all this is done, we will recapture the QDA graphs. So before we can continue to serve requests. So basically, this means the downtime all goes into a particular model forward step, and this would cause, for example, the existing worker goes down for 1 or 2 minutes or even longer, and this would cause later request to accumulate in the queue, delaying the completion of all requests. To understand the cost, let's first say the cost, scale up cost from 2 GPUs to 4 GPUs of the Qwen 3 30 billion models. Basically, as we can say, the cost to reinitialize the communicator and transfer weights is actually quite small. We know that here touch compare has a little bit of cost. This is already we directly lose the compare result from disk. But anyway, this is probably due to the cache is located on a remote storage, so it still has some kind of cost. But still, as we can see, the majority of the overhead happens in recapturing all the QDA graphs, and the capture cost increase with the model sizes. And this cost is already, I think, optimized over the past few months by vLLM. And before that, I think a few months ago, the capturing cost during graph capturing, we need to do a lot of garbage collection in Python, and the capturing cost can be 0 minutes even for DeepSeek model. Yeah. To understand why QDA graph capture is costly, let's say what is happening under the graph capture. So when vLLM is doing the graph capturing, it will basically wrap the model forward under the PyTorch QDA graph manager context, and it will basically call the QDA APIs to do the begin capture and end capture. And what actually happens is the entire model forward logic is executed just without executing any actual kernels. Basically, this means we are essentially executing the model forward without the QDA graph. That is basically the cost. And graph capture is slow because the CPU operations themselves are slow. This is exactly the same as we can say if we are doing NVTX analyze over that. Basically, we can say there's a lot of bubbles between all the QDA APIs because CPU operations are very slow. This is why we need to use QDA graph to avoid this cost as decode time. And after we get this sense of why graph capture is slow, let's say why we need to actually update the QDA graph. Because actually in decode mode, the export modules have a compute buffer size that is basically proportional to the GPU size in the inference group. And after the EP size is changed, we may have different QDA graph topology and different QDA kernel function implementations for the optimized for the particular compute size. And we also need to reallocate the compute and communication buffers for these kernels. And so essentially, we have changes in both the graph topology, the kernel functions, and all the buffer pointers. And so there's one optimization we can do. We can enable incremental graph updates. What this means is we can amortize the cost of recapturing or updating the QDA graph of different batch sizes into multiple model forward iterations. For example, when we encountered a batch size of B, and we need to serve with this kind of graph batch size. If the batch size the graph for that batch size is not already updated, we can still use the old graph with the original set of GPUs to compute the model forward. And if the graph is already updated, we just switch to a new configuration. And so with this kind of incremental QDA graph updates, we can actually enable progressive reconfiguration. We can actually break down both the weight sending and also the graph update and all other costs into multiple model forward iterations. And this will actually have a benefit that, for example, without this kind of progressive reconfiguration, we will pay a heavy upfront downtime that would delay the finish time of all the in-flight batches. But with the progressive reconfiguration, the execution time of each model forward step will be delayed a little bit, but the average job completion time of these in-flight batches can be significantly improved, as we can see. And another optimization we can do is we can know that actually only the subgraphs of the MOE blocks are changed upon scaling up and scaling down, because attention part is purely data parallelism, or it can be combined with a small tensor parallelism. Anyway, the attention part is not changed at all. So we actually don't need to recapture the attention parts computation, and we don't need to allocate the compute buffers for the attention modules. And finally, we also need to solve the fast bootstrap of the neural workers. The neural workers also need to, this is what we already done. We basically let it fetch attention weights and expert weights from PR GPUs instead of remote storage. And we can say even the GPU is, even we need to transfer the entire content of the GPU memory, even over RDMA, we can say the transfer time is still very fast, about 2 to 3 seconds. And this is way faster than, let's say, fetching from remote storage. And we can probably catch the touch compare binaries and all the JIT kernels, for example, for DeepJam, for all possible EP sizes. So we do not need to do JIT compare from scratch. And potentially, we can also materialize all the QDA graph. This would also solve the problem of reconfiguration on the neural workers. We can just load the materialized graph from disk. And here is the overview of our roadmap. So currently, we already have the basic functionality of elastic scaling implemented, and we are currently working on the optimizations we previously talked about. And in the future, we will work on extensions on this framework, like fault tolerance. How can we continue to serve requests with some GPUs disabled? And how can we replace the faulty GPUs when they become available? And how we will also build some kind of scheduling capability over our framework. How can we automatically trigger scale up or scale down based on the current online load? And how can we optimize the serving cost given the current performance goals and the current load? Yeah, and that will be all. Thanks, everyone.
We have some time for questions.
Thanks for the talk. One quick question. I think I'm just missing a bit of context. I guess I don't know how often I should expect these resizings to happen, or I'm trying to motivate for myself why I would want to optimize this, in particular because these layers are also alternating with the attention layers. So it seems like even if you speed up or speed down the expert parallelism, you're still kind of going to be limited by throughput by the attention. So I guess I don't know the relative kind of timescales that you're saving by doing this.
Oh, as we can see from this example, the attention, I think, is purely data parallelism. At least
great.
This is aligns with the case of DeepSeek's official deployment scenario, right? So when we scale up, we're adding one more GPUs or one more data parallelism group, and this means we're adding both the computing capacity to the attention layer and the MOE layers. And we're also scaling up the attention.
That makes sense. Thank you. And then how often do these resizing events happen in your architecture?
I think this actually depends on the online load, right? I think because we're actually adding GPUs, we can actually adding GPUs one by one, right? We can achieve very fine-grained scaling to the online load, right? I think the online load has some kind of a bursty pattern that can change as frequent as several minutes.
Can you give me an intuition for when data parallelism or pipeline parallelism might be better than expert parallelism? Like in what situations expert parallelism is better?
I would say in almost all cases, because expert parallelism is used so that we can achieve a very large batch size for each of the expert to greatly enhance the gem kernel's efficiency. I think with pipeline parallelism or purely some kind of tensor parallelism, we definitely cannot have this kind of benefit.
So I also wanted to add on to that. For tensor tensor parallel and pipeline parallel is orthogonal to EP. We can use both of these techniques. And for DP, it's like closely coupled with EP, and we essentially use both often the time.
Is there any performance difference between capturing graph from scratch and updating the part of graph?
Building what?
Building the CUDA graph from scratch and updating the partial graph of the graph?
Oh, you mean yes. Actually, CUDA actually provides us some API like CUDA graph add node, this kind of API to let us manually construct the graph. But you wouldn't know which node to add, which kernel to use without actually run the model forward, because in Python, I think everything is opaque. And actually, graph capturing is slow because Python CPU operations are slow.
Okay, thank you.
Hi, thanks for the talk. A little bit of a novice question. So you sounded to me, and again, not being an expert, that a lot of this optimization is related to CUDA graph. And CUDA is a part of the NVIDIA GPU stack, essentially. So my question is, if we run a cluster on non-NVIDIA hardware, such as Trainium, Inferentia from AWS, will it all be applicable at all? And if not, do you have plans to extend similar logic to optimization of non-NVIDIA stacks?
Oh, yeah, I think that's a good question. Yeah, I think a lot of our optimization targeted for CUDA graph, but this will definitely also apply to AMD GPU or other kind of GPUs, right? And I think I'm actually not that familiar with the architecture of, for example, Inferentia or TPU, right? But I imagine there would be similar things, right? We are using CUDA graph because we want to minimize the overhead on CPU.
So in other words, yes, you will...
Yeah. Right, it applies to other platforms.
Yeah, I just wanted to add on that. I think there are very similar concepts in other architectures. I heard about the Ascend. They have similar CUDA graph counterparts. And they were in discussion with us about potentially using the same technology for the scaling up. Yeah.
Thanks for a really lovely talk. It seems like there's a balance that we have to strike between targeting stability and efficiency. How do you achieve that within the Elastic Expert framework?
I'm kind of curious, what do you mean by stability?
The chart that stood out to me was where you had laid out when you deploy with Elastic Experts that the time to deployment is shorter, but then the actual execution time takes a little bit longer. Is that sort of a fluid balance, or is it is that just the nature of using Elastic Experts?
Oh, you mean actually this kind of delay of each model forward step, this only happens during reconfiguration. So during normal execution, I don't think there's any overhead on the data path. Yeah.
Thanks. It's a really nice talk. So I think in one of the slides you did discuss about there's this materialized CUDA graph, where it seems to me that you're doing some pre-capturing and store it in the disk. So how would that be different from like capturing in flight, and why can we just not capture like all the CUDA graph for all possible scaling configurations?
You mean let's say we capture that in the beginning, right, upfront. Then let's say for all possible EP configuration, let's say you want to capture it before you are running actual model inference, right?
Yes.
This would actually require, for example, you must keep this inference process, this VLLM process alive during the whole time, right? If the VLLM process is done, you basically have to recapture all the configurations. And if you actually want to capture all the configuration, I probably imagine it to be 1 hour or maybe even longer. Yeah.
I see. So it's basically trying to bring up the service faster kind of thing so that we don't capture all this initially. I mean, is there any way that we can persist this? I'm not expert in this, but just asking.
Yeah, actually the QDA graph just contains of, for example, the graph topology, the kernels, right? What the kernels you are calling, and the kernel parameters, right? We just need to materialize this kind of structure, and for example, the QDA binaries we use. Yeah, and and I would like to add that besides that, for example, even if you want to, let's say, capture all the potential QDA graph sets initially, and potentially you need to keep a standby process to the maximum number of possible GPUs, right? You need to have you need to have standby process that already have the graph when you're scaling up, and we also this would also have some kind of memory issues, I think, because you're capturing a lot of graph, and each graph will allocate internal memory buffers for its intermediate activations.
Thank you for a lovely talk. Just quickly want to check that you mentioned about some timelines that for the CUDA graphs it's almost 45 seconds, for other 10 seconds. So after this one, what is the scale-up time reduced to? It's like less than 30 seconds, or what is
First of all, this 45 seconds is only a very small model. Let's say this is only the Qwen 3 model. This is very small, and the capturing size also increases with the model size because you have more CPU operations, more layers. And I think with our optimizations, if we are doing incremental updates, we would not actually reduce any of the costs, but we'll actually amortize them over multiple iterations. We do not, so the existing requests will not be delayed very long.
Okay, final question.
Hello, thank you for a great talk. I have a question on how do you handle network failures or network congestions during the weight transfers? And also, do you any plans for supporting RDMA natively for this elastic heap?
You mean, I'm not quite get what do you mean by supporting RDMA? I think currently we are already transferring with using RDMA or NVLink. No. Yeah. Otherwise, it wouldn't be that fast, right? And right. And we didn't currently consider failures in both of the weight transfer or, for example, the model execution. Yeah, but I think to support the attention, failure detection and failure handling, we probably still need to have some of mechanism to do to detect, for example, timeout or things like that, and we can retry or maybe to just reconfigure it. Yeah,
so I think the one next step is to integrate with some of the kernels that already handle those fault tolerance, which can, for example, detect the timeouts and mask out some ranks, or it can increase and dynamic increase and decrease the ranks. Yeah, that will be the next step.
Okay, one last round of applause for our speakers.